For over 2 decades, Western dominance in aerial combat was underpinned by the early adoption of active electronically scanned array radar systems. These advanced sensors do not rely on a single moving antenna, but utilize over 1,000 tiny transmit-receive modules acting as independent radars. In legacy Western platforms like the early F-35, Eurofighter Typhoon, or upgraded F-16 variants, these critical modules are constructed from gallium arsenide. While this material was a revolutionary breakthrough at the turn of the century, it possesses severe limitations in modern electronic environments. The contemporary air power matrix has shifted fundamentally because China altered the underlying material composition inside the radar chip itself. Moving beyond simple software optimization, this semiconductor revolution directly targets the core physics of radar energy generation. By transitioning to gallium nitride, modern fighter platforms can achieve unprecedented detection ranges against increasingly stealthy targets. This shift allows a more cost-effective single-engine fighter to effectively match or exceed the sensor performance of heavier Western legacy jets. Consequently, the global defense community is forced to reevaluate structural air superiority through the lens of advanced materials science. Understanding this electronic evolutionary leap requires a strict technical assessment of semiconductor properties under extreme operational stress. The foundational difference between legacy and modern airborne radar architectures lies in the electronic bandgap of the semiconductor substrate. Gallium arsenide is classified as a standard bandgap material, which limits the total amount of voltage it can safely conduct. When operators attempt to push higher electrical current to detect distant targets, legacy modules experience rapid thermal degradation. This physical vulnerability means that traditional transmit-receive modules risk melting if operated at peak capacity for extended durations. To prevent catastrophic hardware failure, Western engineers were historically forced to throttle radar power and accept reduced tracking envelopes. Gallium nitride addresses this limitation directly by functioning as a robust wide-bandgap semiconductor with superior atomic bonds. This advanced material can withstand roughly 5 to 10 times the electric voltage of traditional gallium arsenide before breaking down. Because the atomic structure remains stable under extreme electrical fields, engineers can drastically increase power input without damaging the sensor. This high-voltage resilience fundamentally rewrites the rules of radar design by eliminating the structural vulnerabilities of older generation chips. Ultimately, the transition to wide-bandgap physics transforms the radar from a passive tracking device into an energetic battlefield asset. This advanced atomic resilience translates directly into massive gains in power density within the limited space of a fighter's nose cone. A standard gallium arsenide module typically outputs between 10 to 15 watts of raw radio frequency energy during combat operations. Conversely, a similarly sized gallium nitride module can easily generate 25 to 40 watts of sustained electronic output. When multiplied across a large array containing over 1,000 individual modules, this disparity results in a massive multiplication of total radar power. This staggering increase in energy output allows modern aircraft to achieve vastly superior detection ranges against low observable threats. Beyond raw power output, modern wide-bandgap radars operate with a significantly higher level of electrical efficiency, exceeding 50%. Legacy systems convert approximately 70% of their input energy into waste heat, requiring heavy and complex liquid cooling networks. Because modern modules convert more electricity into functional radar beams, they generate a much smaller thermal footprint during active tracking. This thermal efficiency enables aircraft to deploy highly powerful air-cooled radar arrays, reducing overall weight and airframe maintenance requirements. Consequently, fighters can maintain peak operational output longer without risking sensor burnout or straining internal cooling mechanisms. While Western militaries initially focused on qualifying wide-bandgap semiconductors for large naval ships and ground installations, China prioritized its fighter fleet. Led by the state-run China Electronics Technology Group Corporation, the domestic defense industry integrated these advanced sensors directly into tactical aviation. The export-oriented J-10CE fighter showcased this trend early on by adopting an active array configuration widely believed to utilize gallium nitride. This rapid industrial implementation allowed a lightweight, single-engine aircraft to achieve a significant increase in peak power over legacy variants. This aggressive deployment strategy successfully closed the historic sensor advantage, long maintained by premium Western fourth-generation combat platforms. Following the early testing phases, China systematically expanded this advanced radar architecture across its entire heavy fighter spectrum. The fifth-generation J-20 heavy fighter is highly likely to have transitioned to advanced wide-bandgap arrays in its newer operational variants. Concurrently, specialized platforms like the J-16D electronic warfare jet utilize high-power pods to generate immense disruptive jamming signals. The newly developed J-35 carrier-borne fighter was designed from its inception around this high-output semiconductor baseline to maximize carrier group defense. By building a unified high-volume production line, China established a first-mover advantage across multiple distinct tiers of its air power matrix. The delay in Western adoption of airborne wide-bandgap radars stems from strict institutional certification standards and immense legacy infrastructure investments. The United States military requires extensive long-term reliability testing before cleared avionics can be integrated into frontline combat assets. During the initial development phases, early wide-bandgap modules exhibited high fragility that conflicted with rigorous Western safety margins. Furthermore, defense giants had already invested billions of dollars into massive production foundries optimized exclusively for older generation materials. Scrapping these operational assembly lines to build completely new semiconductor infrastructure presented a severe financial and logistical challenge for Western manufacturers. It is critical to note that the United States successfully deployed gallium nitride at sea via the AN/SPY-6 radar in 2016. However, scaling this high-power technology down into the tightly constrained nose cone of a fighter aircraft presented unique engineering hurdles. Airborne radar arrays must operate under extreme G-forces, intense vibrations, and highly limited cooling capacities without heavy liquid pumps. While Western frameworks chose to rely on mature gallium arsenide networks, supported by specialized electronic warfare fleets, China accepted higher deployment risks. As a result, the United States is only recently introducing comparable airborne capabilities through the F-35 upcoming block upgrades. Real-world tactical consequence of this technological shift manifests as a fundamental redistribution of electronic warfare capabilities. In highly contested environments, the massive power output of a modern radar can effectively burn through hostile jamming attempts. This high energy density enables the sensor to maintain target tracks, even when facing sophisticated electronic countermeasures from peer adversaries. Furthermore, the expansive operational bandwidth allows the radar to shift frequencies instantly across a wide electromagnetic spectrum. This rapid frequency agility grants the aircraft true low probability of intercept characteristics, masking its active emissions from enemy warning receivers. This sensor superiority also supercharges the lethal envelope of long-range air-to-air munitions like the active-guided PLACE-15E missile. This sensor superiority also supercharges the lethal envelope of long-range air-to-air munitions like the active-guided PL-15E missile. The high-power radar array provides ultra-precise, continuous, mid-course guidance updates to the missile over extreme operational distances. This accurate data transmission ensures the weapon maintains an optimal energy state before activating its own terminal seeker. During complex multinational training maneuvers, this continuous electronic tracking capability alters the historical balance of beyond visual range engagements. Therefore, materials science directly determines whether a modern fighter can effectively dictate the terms of aerial combat. Evaluating the true maturity of any advanced technology ecosystem requires looking beyond final assembly lines into the raw mineral supply chain. The production of wide-bandgap semiconductor wafers demands an incredibly pure supply of primary gallium refined to extreme industrial standards. China currently controls approximately 98% of the world's primary gallium production as a byproduct of aluminum processing. More critically, Beijing commands roughly 85 to 90% of the global high-purity refining capacity required for actual semiconductor manufacturing. This near-total consolidation grants Eastern manufacturers an unmatched logistical and cost advantage over international competitors. Beyond gallium, a modern military radar array relies on a complex matrix of other highly controlled critical minerals. Elements like indium are essential for integrating advanced infrared search and track sensors alongside the primary radar array. Furthermore, next-generation radar research heavily depends on scandium to develop advanced aluminum-scandium nitride substrates. Materials like boron nitride also serve as vital thermal insulators to manage the intense heat generated within each module. By dominating the extraction and refinement of these specific elements, China maintains a powerful chokehold on future electronic warfare components. This total consolidation of critical mineral processing gives Beijing an immense strategic lever over the global defense industrial base. The implementation of strict export licensing requirements on gallium and germanium directly targets Western military modernization programs. Major Western defense contractors have reported supply chain frictions and material acquisition delays following these regulatory changes. Because Western manufacturers cannot easily source these refined elements elsewhere, production timelines for advanced sensors face continuous pressure. This regulatory bottleneck demonstrates that achieving military innovation is meaningless without secure access to the necessary raw material baseline. The economic disparity created by this monopolization further enhances China's domestic defense production advantages. State-run institutes can source primary gallium at stable, subsidized domestic prices, while Western firms face volatile global spot markets. This cost advantage allows Eastern manufacturers to rapidly iterate, test, and discard experimental radar configurations at a fraction of Western costs. For international export clients, this economic efficiency translates into premium combat capabilities delivered at highly competitive prices. Consequently, mineral control functions as an active weapon that slows Western upgrades while accelerating Eastern military proliferation. The final evaluation of the semiconductor race reveals that the era of low observable aircraft is far from over. The F-22 Raptor and F-35 Lightning II continue to maintain a highly dominant position in modern operational doctrines. Airborne wide-bandgap radars offer significant tactical advantages, but they do not automatically render established stealth platforms obsolete. China's rapid industrialization has certainly shortened the global technology curve, but it must still contend with the limits of operational endurance. Therefore, the current state of air power remains defined by incremental engineering upgrades rather than a sudden materials revolution. True military superiority will not be secured by a single revolutionary sensor or an impenetrable invisibility coating. Victory in a high-intensity conflict depends entirely on the robust integration of a comprehensive system of systems architecture. The nation that successfully links its radar arrays, satellite constellations, electronic warfare nodes, and kinetic platforms will control the battle space. While advanced materials research will continue to generate fascinating headlines, practical deployment on the battlefield remains a multifaceted challenge. In this ultimate technological duel, structural engineering and system-wide networking continue to outpace the promise of any singular breakthrough.